Good morning, everybody, to our EARTO webinar series on standardization in research and technology for practitioners. My name is Knut Blind, and we have today the third event, which is going to really focus on the topic research and standardization. And I hope it's not too dense, because I have to admit this is a little bit my hobby horse of the last more than 20 years. Background is the EDU4Standards project, where the overall objective is really to empower standardization through education in Europe. And here we have a different objective: creating material, having academic standards at universities, increasing the number of universities offering teaching, kind of getting more teachers to offer courses, and also have more students, and also set up a student association. And within this project, we have produced a teaching concept, content, and we are running pilots. And the event today is part of the EARTO pilot, which is kind of focusing on people working in EARTO institutions. The other pilots are addressing more the students' bachelor, master level, etc. Target groups, we have six modules. The two first ones, we're really focusing a little bit on the basics. How does the standardization landscape look like? Which type of different organization do we have? How do they work roughly, and not in detail? The second one was a little bit about the generic impact dimensions of standards, their functionalities, like compatibility, quality assurance, variety reduction, and also the provision of information. This part will be kind of integrated in today's lectures. But today it's really addressing researchers, and especially the interface between research and standardization, but also how maybe standards help researchers in doing their work. And this will be then continued next week with a stronger focus on the role of intellectual property rights, especially patents. We already mentioned this today, but this will be then further elaborated next week. And this is the agenda. And then in 2 weeks' time, I have the pleasure to have the head of Linux Europe, of the Linux Foundation, Mirko Böhm, with us, who will focus on the interface between open source and standardization, which is a new topic. And finally, we conclude this series with a lecture on the geopolitics of standardization, but also addressing European interests and values. And here, Barbara Reiter from the University of Graz will join me. But now let's get into today's topic, which is research and standardization. And we start a little bit with some, I don't know, boring, but I think it's a little important to understand how research and development is defined, and then we go into the interlinkages between research and development on the one hand, standardization on the other hand. And then we also look on the impact of standards on research and innovation, but also the impact of standardization processes, which is a little bit a new additional development. Regarding the readings, these are the basics. The Etsy book kind of already has incorporated some of my stuff. More recently, I put something together for ISO, which is also publicly available on standards and innovation, which is kind of the state of play collected until 2020. But as you will see in the references, there's much new work. I will also kind of refer to and have integrated. What is the objective of today? We have the following learning objective: really to learn more about this interface between research and standardization, especially the interdependent relationships, because I think here it's not clear how really close and partly very complex the interaction is, and also how the two different activities might benefit from each other. And then also how do we get research insights into standardization, which is also from a researcher perspective, I think an interesting and relevant topic. But also to learn a little bit how our standards can support your research. Now, about the definition, research and development is defined since several decades, meanwhile, by the OECD and in the so-called Frascati manual. And the last edition is now already, it's 10 years old. I'm not aware that there will be a new one, but it says that research and experimental development, R&D in short, comprise creative and systemic work undertaken in order to increase the stock of knowledge, including knowledge of humankind, culture, and society, and to devise new applications of available knowledge. The basic criterion for distinguishing the R&D from related activity is the presence in RSA of an appreciable element of novelty and a resolution of scientific and technological uncertainty. That means when the solution to a problem is not really appealing to someone familiar with the basic stock of common knowledge and techniques for the area concerned. That means it's a systemic approach to problem solving. And within research and development, we are making three or four distinction parts. Basic research is really very experimental and theoretical, and it's really just about acquiring new knowledge of the underlying foundations of phenomena and observable fact without any particular application or use in view. And within this basic research, the OECD differentiates between really pure basic research, which is really just about creating new progress in knowledge, really without having specific economic or social benefits in mind, and also not the idea to transfer these results to sectors or to specific applications. The oriented basic research, there is already a little bit the expectation to produce something which might likely then to be the base for solving future problems. And that leads us to the next element of research, and that's applied research. And since we are EARTO researchers, we are more on this kind of type of research focused, because here it's really directed to specific aims or objectives. It means new methods to achieve specific objectives, reducing climate change, reducing maybe also waste, increasing efficiency. And we might rely on the insights from basic research, but that's not necessarily the case. And in contrast to basic research, where the new insights are in general quite kind of broadly applicable, here in applied research, the findings are very specific, often to specific sectors, specific companies, and very specific maybe technologies. The last step is experimental development. Also, I think quite a number of EARTO researchers is doing experimental development, but in general, this part is more located in companies, because here this experimental development is drawing on the knowledge gained from basic research, applied research. And here the objectives is really producing products, generate new processes, or improving what's already there. That's the point. The general criteria for R&D is really the novelty aspect, also the creativity aspect, because it's based on not obvious concepts and hypotheses. There's some uncertainty, and it should be systematic. That's also important. and the results might really lead then to transferable and reproducible insights. That means you can also then repeatedly do that. That's R&D, and now to make the distinction, what is not R&D? Education and training. That means what we are doing today. Also scientific and technical information systems like library services, patent services, the admin. That means do the admin of the finances. Then also specific industrial activities. That means just the implementation of a new or improved product is not Richard. Big data project for dissemination of data and space explorations. That means the expenditure for satellites is also not R&D. Then there are some borderline activities. Prototyping might be included in R&D, pilot plans, also industrial designs, industrial engineering and tooling up. Here the activities might be split into R&D and not R&D, but it should be included all the pre-production development, after-sales services, patent licensing works, routine test, data collections, and routine compliance with public inspection controls, enforcement of standards. That means if you do something in order to comply to a standard or to a regulation, this is also not R&D. And now, finally, testing and standardization. And the OECD says in a 2002 document that this concerns the maintenance of national standards, the calibration of secondary standards, and routine testing and analysis of materials, components, products, processes, soils, and atmospheres. And in the Frascati manual, it says public bodies and consumer organizations often operate laboratories that are intended to manage test products and verify that standards are met. And in addition to standard testing, benchmarking activities, which are not R&D. That means if you do testing, this is not R&D in the OECD sense. But if you really spend time in devising new or substantially improved testing methods, such activities should be included in R&D. That means work which lead then to better standards are definitely defined as R&D. And this brings us to what or how I see this interaction, and we developed within I think FP5 or FP6 project this following kind of simple model of research and standardization, where we have first research and development, and then on the other hand standardization, and there's this knowledge and technology transfer from research to standardization. That means research results might go into standards. There might be also a pull. That means if standardization committees require new insights from R&D, that's this one kind of relationship. There are different barriers. We are not talking about them today or only partly, but they might exist. But there's also this recourse of knowledge and technology transfer, because standardization creates standards, and these standards might be then really the base for follow-up research activities. And sometimes maybe also researchers require the development of new standards in order to make progress in their work. That's from a conceptual perspective. Recently, 2 years ago, we conducted the first European standardization panel. And here the question was, what's the input into standards? You see here the three top kind of input sources for standardization is policy and regulation. That's for companies important, the requirement of customers, and that was quite interesting and surprisingly for us, that more or less equally important is also the own research insights are integrated into standards. In the probably maybe next week or 2 weeks, I will share a link to the second edition of the European Standardization Panel, and I will also urge you to maybe participate, but also distribute that. That's a side note. More about that probably next week. Now, from a conceptual perspective, we have also then introduced or implemented this technology transfer model, which has been developed by Barry Boozman in I think 2000. That means 25 years ago, where he kind of developed a kind of a cascading model, and we argued, and we also kind of argued with him directly that standardization might be also a very specific but important technology transfer channel. That means what we do in research is we produce knowledge, as we have seen before, and this leads then to the transfer medium, publications, patents. Nowadays, maybe also social media activities, internet blogs, etc., etc. And this might be then get into standardization. There are different ways. The standards bodies and the technical committees and working groups might really maybe read the literature, maybe screen the patent landscape, but also maybe researchers get directly involved. That means the standardization process does create consensus and coordinates things, and the output are standards. And at the end, these standards are implemented, and we know also from a survey we did that if researchers are really involved in standardization, a big majority is then also able to implement the standards in their organization. But there are feedback loops, both from standardization back to research, as we will see later. It means there is indeed then maybe the requirement to conduct new research because maybe something is not going to work when you start the standardization work. That's the one feedback loop. From the implementation perspective, which is for us as researchers not so relevant, although as you will see later, we also kind of implement some standards. The implementation might lead to the need to redefine the standard because maybe it doesn't work the way we wanted to have it. It's maybe not doable, inefficient, too costly, etc. But it might also lead then to the insight, okay, we need more research because the implementation of the standards kind of created or showed Sorry, I'm back. I don't know what happened. I was kicked out. And I start sharing again. Oops. No idea what happened. Sorry for that. Oops. Okay, where we were. Okay. I hope you see my screen. Okay. This is an example of an analysis we did based on the information of researchers active at the German Agency for Material Research and Testing here in Berlin. And what you see is the following distribution, that they have 600 researchers, and the majority of them are publishing. Some are doing patents, and some are doing standardization, and there are kind of 34 people who are doing all three things. That's means. But it shows that research in general are not really into standardization. That's one insight, and we have also from other organizations this information that only a very small share is really active. However, and that's maybe also an interesting figure. This is data, and this is representative data for Germany about innovation in the German industry, and we have around 3,000 observations beyond this figure. And what you see is, and that's really a shift. This is data from 21, I think, 21. That meanwhile, and these are innovative firms. 75 do nothing. In the sense of publishing, patenting, and developing standards, but 10% of the innovative firms, or 12%, are really involved in standardization. And but only less than 8% are involved in patenting. 20 years before, this was really different. That means we see really a shift. Companies are getting there. And that's maybe also an important insight. And what we also see is around 5% of the companies are doing both. That means they file patents, and they really are involved in standardization. The number of companies publishing scientific papers is quite limited, as you see here. Coming back to, I'm just jumping back to this picture, where we see, okay, standards can refer to scientific publications and can refer to patents. And what we did is we looked at this phenomena, and here this is a case from biotechnology, where we see then, if you get your publication, your paper cited in a standard, this is outperforming kind of similar publications. This is a very specific and small scale case. What we just published, and this was out, I think, since Monday, therefore very new stuff, is we looked at all scientific publications which are referenced in ISO standards. And what you see is above that, in general, these, and we call them standard relevant publications. And you see, in general, they are outperforming the citation patterns of control groups. And that's true for all publications. And then we distinguish then between papers which are already, before they are cited in the standards, are highly cited, and they are even more better performing. But we also look at the low cited standard relevant publications, and they are still outperforming these these control groups. Now, last information about this. If we are now looking at what was before and after, we see a little bit that in general these publications are better than the control group when they went into standards, but after standardization, the outperformance is only limited to a very short time. This might be at first glance be not very convincing and positive, but this also shows that the feedback loop from standards back to research is limited. In contrast, and that's the other kind of opportunity to claim patents to be essential for standards, and that's the ICT world. Whereas these publications cover all areas in the ICT world, we have the phenomena of the so-called standard essential publications. Here we see definitely that these patents are outperforming control groups, and colleagues from Boston, Weissman Simcoe, did that 2008, and this was recently confirmed by a colleague Rudi Beckers from Eindhoven University, where you see that the declared essential patents are outperforming the others, the control group. But if you are looking at specific technical committees, and here ETSI, ANSI in US, IEEE, they are depending on which kind of organization and which group you're looking. The outperformance is a little bit better or worse. But in general, this is a clear pattern. That means here these patents are much more valuable than control groups. Looking at the comparison. For standard essential patents, we have really since more than 20 years a very established process. We have to declare them. Regarding the scientific publications, the process is a little bit obscure. It's not really very clear. It depends a little bit on how many researchers are in the technical committees, but the organization have not yet a specific approach to that. Interestingly is that the patent process, and we will talk about this next week a little more in detail, and the standardization process interlap, whereas regarding the scientific publications, they have to be published and then they are cited. In general, it's more applied research. The areas, the standard relevant publications cover all areas, but there's a focus on health, safety, and environmental standards. Standard essential patents is ICT, or even in narrow sense, mobile communication. What are the actors? The standard essential patents are owned in general by companies. In some research organizations, including Fraunhofer, the famous MP3 story has here to be mentioned, but the scientific publications are generated by researchers. Some company publications are also matter. The researchers are in general later in their careers, that we know, and the motivations, standard essential patents is really a strong commercial interest, also maybe a signal interest, and also maybe the interest to create some freedom to operate. If your patent is referenced in a standard, the motivations for the researchers is much more intrinsic, reputation, but also influence public policies. Because especially if these standards are referenced in standards which are linked to regulations, then you really can also shape the regulatory framework. The barriers would cost of participation, and that's a big problem, is the lack of recognition in the scientific community, and therefore we want to show evidence that really it also really pays off, in the sense that maybe you get higher cited papers, and that's the case. That means the selection effect is clear. The standards bodies and technical committees select the highly cited stuff. The follow-up kind of effect is a little bit more mixed regarding standards essential patents. It's clear, and they have also positive commercial impacts, regarding our standard relevant publications, we cannot say that. Okay, that's about publications in standards, patent standards. Now, what we now doing is looking also what could standards do for your research. And here we come back to the different functionalities of standards I introduced already last week. Means management safety and quality standards, compatibility standards, variety reducing standards, and information and measurement and testing standards. That means a little bit more explicit to research. These quality standards reduce the information asymmetries and help to increase the trust and confidence of the buyers in order to make sure that we also have kind of high quality products in the market. And we see these safety standards for car safety, for example, in food, that's playing a role. The other next type is compatibility standards, especially in the IT world, because network effects are key for innovation to be successful. And then we have the variety reducing standards. That's more for the commercial world, maybe not so relevant for us, because here they really push mass production, scaling down the cost curve. This is not so relevant for us. For us as a researchers, information measurement standards are key, and I will provide you now with some examples where this play an interesting role. Because here, it really helps also the communication among researchers. It means measurement is key also for engineering, etc. And bringing all these different types of standards into the logic of the different phases from research, pure basic research to really the commercialization. We kind of developed this figure because this research was also a little bit triggered by the perception 20 years ago that, okay, you do the research, and when the research is finished, you think about standardization. No, that's not really the right way to do it. The right way to do it is really to consider standardization much earlier in the research process, because even in basic research, it's really about defining terminology. That means the semantics has to be cleared at the very beginning. Sure, we do that in our research, in journals, etc., to start to define concepts, terms, etc. But this should be then also early reflected in standardization. This is in general in the basic research area. When we move from basic research to applied research, then measurement and testing comes into play. In order to make progress, we have to measure things in order to make research replicable and to validate that. Therefore, this is key. And then when applied research then is moving really to experimental development to specific products, and interface standards are becoming relevant. And when you're entering into the market, the issue of quality comes into play, maybe also variety reducing. That means at the very beginning, it's about reducing information and transaction costs. And then later, the interface standards, then it's about interoperability between components. Therefore, think about maybe a new chip you want to embed in a complex system like laptop or mobile phones, etc. Then this has to be interoperable with what's already there. It means we save the adaptation cost, maybe also avoid to use converters, etc. And then towards the market, it's about quality, it's about health, safety, and privacy risk. Also important. Creating critical masses allow economies of scale, create network externalities, and also the interoperability between products or between products and systems. That was the approach we applied. Now nowadays, if you especially think about your maybe Horizon project, here the other kind of taxonomy are the technology readiness level, TRLs, from 1 to 9. from knowledge development, technology development, business development. But also here, they took kind of our idea and said, okay, at the very beginning, we need semantic standards to facilitate the communication. Then measurement and testing standards for applied research. Experimental development requires then interface standards in order to assure interoperability. And then when products are brought to the market, here specific performance issues and especially quality and safety are key. Now, is that really then the case? And we did 20 years ago this focus on nanotech, and here are examples where in the early stages when the nanotech technical committee was created at ISO, they started with really defining these terms. What is nanoscale? Is it 1 nanometer, 100 nanometer? And then there were kind of standards which define nano-object, particles, plates, cylinders, etc., etc. It means this was really then done in 2005. And by the way, this was then considered as being quite late because the research in nanotech started already in the 90s. And here nobody thought about standardization, but this has meanwhile changed, as I will show you in the next slides. The other topic was measurement, and here nanoparticles are kind of really a very nice example how important measurement is important. And this is just a kind of an illustration how you can measure things, and it's about measuring lengths, weights, sedimation rates, diffusion behavior, etc. That means you have to find an agreement because otherwise you are really at the end comparing maybe different measurement results which are maybe different because you are just applying different measurement approaches, and that's very important. Another, because this is meanwhile a historical example, a much more kind of recent example is now quantum. Quantum technology, and here Senelec also created this focus group, and now meanwhile a technical committee on quantum technology, and there are some topics of what they wanted to do or plan to do. And there's also a paper in the reference list which is explaining that a little bit more in detail. I'm not the quantum expert, but what you see here in the next slide is the roadmap they had in mind, where they say, okay, again, terminology, metrics, test and measurement standards are at the beginning, and then when we start the commercialization. Here, interconnectivity, interoperability are topics which pop up, and then they also already think about mass production. That means again, here you see a little bit this systematic overview of different approaches or different topics along the technological life cycle. Of especially new technologies, and then also for quantum computing, they published this timeline in their roadmap, and that's again here first it's more about metrics, and then later it's more about then quality, health issues, noise performance, etc. Aspects or hardware software interfaces. That means the interoperability comes then into play between different components, which is following a little bit our initial model. And again, what I mentioned, the technology readiness level here, Van Deventer and others, they also then attributed the different standardization activities to the different TRLs. Means here at first they call it standards for science, and here the customer are the scientist. That means you as researchers, you are the scientist, for these standards. And here again, terminology, test, measurement, and then standards for components. Here the customer is the system integrator. That means about interfaces, functionalities, quality issues. And then the last step, they call it standards for systems, where the customer is then the service provider. Here it's about protocols, data, models, etc., which play a role. That means here very nicely also you see the different stages of standardization along the TRLs of a new technology. Means they put that together and try and created this new GTC 22 on quantum technology, where they really push that forward. And here we see also broad involvement of different companies, countries in Europe. And that means very broad coverage. And again, here, the kickoff of this JTC was 2 years ago in Berlin. To conclude, that means you see here, this is really closely interacting the different phases of research and standardization. And this pattern we observed for nanotech 20 years ago is now also visible for quantum. This leads us to kind of the chart I already presented a little bit differently last week on the different functions of standards and the impacts on research and innovation, which might be positive, negative. Means they provide information, and that's important, and therefore also in your research, maybe have a look on the existing standards. Might help also to coordinate the collaborative research and innovation activities. Sure, there is a cost of screening, and the access to standards is a topic. From the industry perspective, there might be also the issue of unintended knowledge leakages and spillovers if you specify the maybe standards too narrow, and if you maybe disclose too much information. Right reduction, economies of scale, especially in new emerging technologies. One time you have to make a decision which kind of trajectory you want to go. And a famous example is again the GSM standard, where there was then the decision, okay, we are going for the GSM technology and not other ones. But if then these standards are created, there are strong incentive for further incremental innovation based on this kind of base standards. Choice reduction is the consequence, is maybe also from a research perspective not always positive, but also in research we make this choice to reduce maybe the opportunities at a specific time. The other aspects are more market related. It might really lead to market concentration. We might also maybe select prematurely technology which is not the best one. That's definitely also an option. This in the GSM case, ex post, it turned out that it was not the best choice, and standards are definitely also a barrier for radical innovation. That's clear. Therefore, if a standard is established, the new radical innovation has to be much better in order to really compensate all the positive impacts of having standards and maybe establish networks and network effects. Quality, trust in innovative technologies is important in order to make them successful in the market. If they are too maybe strict, they might concentrate the market. Compatibility creates variety because you can kind of combine different things, pushes network externalities, which is important for most of the technologies nowadays. And if there's a backward technology to previous backward standards to previous technologies, then maybe logins are avoided. If standards are dominated by specific players, then maybe monopoly power might emerge, which is not good. And Standards might also be able to log into old technologies if the network externalities are so strong and there's no kind of also forward compatibility to the next generation. And the insurance function, which has been introduced by colleagues from Cambridge, Foucault and Lee, they say, okay, yeah, standards could be an insurance against failure of radical innovation. This is especially maybe not so important for us, but in industry, if you know, okay, you can try to innovate, but if it doesn't work, maybe you can rely on existing standards. Therefore, that's positive. On the other hand, it creates a strong incentive for doing more incremental instead of radical innovation. That's the point. So last, this is a little bit a new idea. Transdisciplinarity. What is transdisciplinarity? I do not have time to really go into details of that, but transdisciplinarity means that in general you involve also the object of your research in the research process. And there's some tradition of transdisciplinary, especially in the context of sustainability. And what I see is that standardization is one specific type of transdisciplinary knowledge production and transfer, because the impetus for standardization can come either from practice, mainly from industry, but also from the scientific world. And then you bring different stakeholders together to define the standardization problem. And within the standardization process, you are not only relying on what's already there on the scientific papers, on the patents. No, you also create new know-how within the process and in the working groups. And therefore, this is a kind of a transdisciplinary knowledge production process. At the end, you have a new standard, and this standard might be then implemented on the one hand in industry if it's more kind of applied and maybe manufacturer relevant. And it might be then also create a feedback loop what we had before. Also important is the linkage to the regulatory framework. From the scientific perspective, a new standards might be also the base for your research, might create maybe new scientific problems or challenges, which might be then lead to the next round of standardization. And it means you have these circles, and if it's going to work well, these are not vicious but virtuous circles. And one of my former PhD did some work based on data from the French standardization body AFNOR, where he looked at what's really going on within standardization. And this is maybe the last aspect. That means there's not only the point, okay, there's the input from research into standardization, and when the standard is created, there's kind of the option for researchers to use the standard. No, even within the standardization process, so-called knowledge networks are created, because you are getting in contact with other stakeholders, with other researchers, with companies, with regulators, with customers, with consumer organizations, with environmental organizations, and these are very interesting networks. Which allow you to get access to know-how and technologies which are maybe not in your domain. And you might also be in a proper position. And this might create innovations in the next generation within the standardization process. And we developed kind of two hypotheses. On the one hand, we said, okay, if you go to standardization, you have the option to get really in contact with a diversity of knowledge. In the technical committees, you are active, and the broader this access to, or the broader the portfolio of diversity of knowledge, the better. But you can also create a kind of broker position. That means you are brokering between different kind of knowledge domains, and this is also positive. However, that means the knowledge base is both benefiting from the diversity of knowledge you get, but also maybe from the brokering position. Nevertheless, the point is that if the knowledge is getting kind of too far away from your domain, it maybe doesn't help too much. And if the brokerage position is maybe getting too complex, then the costs are higher than the benefits. And therefore, we claim there's an inverted U shape. And indeed, what we see, especially for the technological distance, if you get into standardization, get really also access to maybe areas which are not really your main domain. But if it's getting too far away from your kind of original domain, the impact on output, and we use pattern application as an output, then it's getting maybe a little bit problematic, because then the costs are higher than the benefits. For the brokerage position, we do not see so much this inverted U shape. That's it so far. To sum up a little bit, looking back at the history of research about the interaction between R&D, patenting, innovation, and standardization, we find already now work which is 40 years old by Al Link, still editor of the Journal of Technology Transfer. He says, okay, the R&D intensity of companies drives their involvement in standardization. A Dutch colleague, he couldn't find some relationship. One of my first studies showed an invert U shape. That means the higher the R&D intensity, but also the export intensity of a company, the higher is the likelihood that it's get involved in standardization. But if they are very, very kind of R&D intensive, then they are staying away. And the point is here that especially companies which are at the leading edge, are not really so keen to share all their insights in standardization. That means there might be knowledge spillovers they are not really happy about. Patent intensity is a little bit ambivalent, but there is a little bit the tension that the higher the patent intensity of companies, the less likely they are to get involved in standardization. Regarding R&D, this inverted U shape is kind of confirmed in different studies, also not only German but also Dutch companies. Regarding entry into standardization, we find a little bit the finding that if companies have kind of a patent portfolio which is quite strong, then they get into standardization also if they have introduced innovations. Here, the colleagues from the UK, Foucault and Lee, they show that standards usage kind of pushes more incremental and reduces radical innovation, which is also an interesting insight. And what we found that based on German data is the innovation intensity of companies, including R&D, is positive correlated with the involvement in standardization. The other kind of observation is, okay, standards might be an obstacle for the innovation process. Here are some statements from other researchers which are okay. In general, if standardization is open and transparent, then this is not the case. Therefore, we have in general a positive relationship. To sum up, definitely research is important for standardization. Therefore, your input is important. We have now, in addition to the standard-centric patents, which are very focused on the ICT and the mobile communication sector as inputs for standards, we also know that scientific publications matter, at least for the ISO standards, which are more or less the gold standard in standardization. On the other hand, standards are a form of codified knowledge. and they help then really to push the dissemination of your research, and might also then facilitate follow-up innovations. But also within the standardization process, knowledge production and innovation takes place. And here the idea of transdisciplinarity might be interesting. And please, if you have critical comments, I'm quite open to that, because this is a little bit a new idea, which might be also maybe nonsense, but I think it's at least worthwhile to think about. We observe both at the individual level, but that means looking at the individual researchers, but also at the company level, a positive correlation between research, patenting, and innovation activities, but also between research, also publication and standardization activities, and what they are doing on standardization on the other hand. However, the clear-cut causality is a little bit difficult, and therefore it's still kind of also a little bit maybe difficult for you to argue against your boss. Okay, it makes sense for me to go there and get involved in standardization, because really that's not so it's not so easy. On the other hand, there is also often or very limited insight whether patenting is really paying off now. But there might be tensions, especially between standards and radical innovation. And also, if you have really radical ideas in your research and go to an established committee, you might face problems. That's an issue. And we also see tensions between standardization and intellectual property rights, especially patents. But this will be further kind of discussed and presented next week when we talk about IPRs and standardization. Thanks a lot for joining, and sorry for the technical problem I had. I don't know what happened, but I think it was an issue. Oh, there was a hand up. Please speak up, or no? I think you can speak or not. Just speak. Or write something in the chat. Unfortunately, while my manager here of the system is not with us. Okay. Or you cannot activate the mic. Okay, we will manage it next time. Yeah, but maybe just try to write something in the chat, and I will answer you. Yeah, thanks a lot, and see you next Thursday. Thank you. Bye.